heat transfer mechanisms. During the first week of class, we discussed energy balances. And it was only balancing our bank account, right? What comes in, what goes out, what is generated, and is equals what is stored. And we saw energy balances that are a batch energy balance in joules. We saw balances of energy rates. In the seminar on Monday, you saw an example. And as I was part of the groups during the breakout rooms, what I saw is that these concepts that seem very simple were difficult to implement. So two things here. As you prepare for the exams, I want to suggest you take a good look at the handout I prepared, and also at the book I very strongly recommend you get. Also, heat transfer, this class, it has something that is unique in your engineering education, and it is that much of what we are talking about, you already know by intuition. That's a good thing. But what we're doing is putting that intuition into a formal framework that is going to help us go beyond the intuition. But the end result is that we're combining the two halves of the brain, an intuitive side of the brain with a rigorous half of the brain. And we need to put it together. So things that happen often is like, for example, we say we put a hot sphere in colder water, and we ask, is there any Q in? And people might say yes, but in reality, the sphere is cooling down, right? So we forget some things that you for sure know, because everybody knows that heat flows from hot to cold. But when we try to make a formal framework, sometimes the gears get stuck. The biggest challenge in this class is not the math at all, but is to be able to put that intuition we already have, all of us, from the time we were babies, into a framework of engineering that is going to help us think beyond. So that would be the name of the game. It's almost like practicing a musical instrument. By practicing, eventually becomes second nature. The language of heat transfer, the goal of this class is that it will become second nature to you. Few things are really new, but we are putting the things you already know in this language that is very powerful. Okay, so about heat transfer mechanisms. Here we go. As a quick review of what we saw when on Monday, we said that in addition of the big Q that is energy, thermal energy in joules, and the small q that is thermal energy in watts is an energy rate. We now have this small q double prime that is a heat flux, and the heat flux can go out of a surface, through a surface, right? And in that case, we call that surface to have a value AS, a surface area, or can go through a cross section of the body, through the inside. That is a case of conduction, and in that case we call it AC. And this is because this is a differential expression, to get a total amount of heat, we would need to integrate over this surface we care about. But for the most part in this class, not always, but for the most part, we're going to say, if we pick the control volume smartly over surfaces that have the same heat flux or the same temperature, very often we can say that the heat flux is constant over that surface, and the integral turns just into this heat flux times area. Then we said, okay, what is the expression of heat flux for the case of convection? And we came up with this formula that mathematically is essentially trivial, but it's extremely powerful. Just as energy balances look like trivial, but last Monday during the seminar, it was not trivial at all. Now we see formulas that look trivial, but they summarize 200 years of research worldwide on heat transfer. And you're getting this cramped to you in 13 weeks, right? So don't be fooled by the simplicity. People thought about this very much before saying it. So we said the key thing here is that the heat transferred by convection is proportional to the temperature difference between the surface temperature and the temperature of the fluid away from the surface. And this constant of proportionality is H, our heat transfer coefficient. Something interesting here, we are not saying exactly what the physics are for this to happen. We're just saying whatever the physics are, the heat transfer by convection is proportional to the temperature difference between surface and fluid. And the way I define it is that it's always positive. So if it is a Q in, Q convection will be positive going in, and if it is a Q out, Q convection will be positive but going out. So when the surface is hot, that would be Ts minus T infinity. When the fluid is cold, will be T infinity minus T surface. T infinity is T temperature of the fluid far away from the wall. And we said something amazing is that despite there are many different fluids with many different properties and many different conditions, overall, we could say that certain types of convection have values that are more or less comparable. And we talked about natural convection versus forced convection, in which in natural convection, there is no external velocity applied to the fluid. And we said in natural convection in a gas, H is more or less 10 watts per meter square Kelvin. But if it was the same case in a liquid like water, it's 10 times higher. Or if it is forced convection in gas, it's 10 times higher. And if it is a liquid and forced, would be 100 times higher. And this was the explanation of why I'm a happy person in a room at 20 degrees C, but I'm a very not happy person in water at 20 degrees C. If you argue that the water is cold, now tell me how the water is colder than the air because both are at 20 C. The real deal is that we're losing energy at a much higher rate against the water because the convection coefficient can be 10 or 100 times higher than me being sitting in the room at 20 degrees C in air. We did a simple calculation that is a ridiculously simple calculation. Please be familiar how to make this calculation because this is what you're going to be doing. Next time you write an energy balance and you say, okay, what is Q in or what is Q out? And Q in or Q out might be by convection. And you will use this equation you saw here. Then we saw radiation. That is a completely different physics. The equation of radiation is at the beginning of the birth of quantum mechanics. It's crazy stuff. But for us, we're not going to do quantum mechanics. We're just going to know that it has a formula in which the heat flux is epsilon sigma T surface to the 4 minus T surrounding to the 4. And for radiation, and only for radiation, we must use Kelvin. For convection or conduction, we can use Kelvin, we can use Celsius, whatever we want. The result will not change. For radiation, it will change. And the reason is convection or conduction are always delta temperatures, relative changes in temperature. But in radiation, we have temperature to the 4, right? It's not a delta T to the 4. No, it's temperature, absolute temperature to the 4 of the surface and the surrounding temperature to the 4. And the complexity of the surface and the way in which atoms emit radiation is all captured in this coefficient epsilon. And we said epsilon can have like two typical values, 0.9 for pretty much everything and 0.2 for clean metals, right? Of course, there are more subtleties, and I even have a book that is only these epsilon values. I have two actually, only that. But it's never going, the whole book never goes too far away from this. So it's good to keep in mind that this is the way it works. And we do the calculation of heat loss by radiation. And what we saw is very simple from the point of view of the math. As long as we remember, in radiation, we use absolute temperature. For everything else is delta T's, and it's the same. Radiation is not a delta T, it's T to the 4. I added this kind of cool chart that is something that people have used since forever, right? We have better scientific instruments now, but imagine you have nothing. And you see a piece of metal that is red hot, and you see it's an intense red or a medium red, but if you get to see that is a relatively like orange red, is at near 100 degrees C. And this is very practical because you start having a sense of temperatures and heat transfer, even having no physical instruments. You do not need to memorize this. I just added it here because I think it's so cool and it's useful in your real life, because you not always go sticking thermocouples. Now, I will go relatively quickly over this other section, but radiation has an equation that is quite different than convection from the point of view of equation, because one is T to the 4th and the other is just a delta T. However, if you remember your early math classes, if you have a fourth power is essentially a square of a square. So the T to the 4 minus the other T to the 4 is 1T squared minus the other T squared. And then we can do the expansion of a difference of a square. You might need perhaps a refresher on this, or maybe you remember this and you think this is obvious. But the cool thing is that this exact equation we had before, this exact equation has this equivalent in which I'm expanding this difference of squares and ends up looking like this. This is exact. This is not an approximation. What is interesting in this expansion, what is interesting is that it ends up having a term that is a delta T, temperature of the surface minus temperature of the surroundings. Has something in the front, but the fact that it has this delta T saying there is no delta T, there is no heat flux by radiation, bigger delta T, bigger heat flux by radiation, means that it's somewhat similar to the equation we had seen for convection. The physics are nothing at all like it. But in the math, we see that there is some similarity in the expression. And we can take that similarity to our advantage, because then we can say Q, the heat flux by radiation, we can call that whole chunk before the delta T, we can call it H radiation. And that would be an equivalent convection coefficient for radiation. By equivalent, I mean it's not convection. Of course, it's not convection. But from the point of view of the math, it looks very much like convection. And the expression of this H radiation equivalent convection coefficient for radiation is this one that we can calculate having the epsilon, the sigma, and the T of the surface and the T of the surroundings. Of course, in convection, the convection coefficient is more or less constant with temperature. Not exactly constant. We'll see exactly how it varies later, but doesn't vary very much. The equivalent convection coefficient for radiation depends very much on the temperature. Check it out. We have it here. So when we do this, it's mathematically exact, except that the H radiation changes quite a bit. However, there's an advantage of doing this, because now if we express it as if it was convection, we can add the surface heat losses by convection plus the surface heat losses by radiation together, right? And in addition, I can do a ballpark of what this equivalent convection coefficient is for radiation. And if we are more or less near room temperature, right, for dull materials like skin or walls or glass, is a value of 5 watts per meter square Kelvin. If you remember, we said that the convection coefficient for natural convection in gases is more or less 10. So what we see is radiation is more or less the same order as convection when we are near room temperature. This matters. And when I finished for natural convection in air, when we were finishing the class on Monday, I mentioned how a thermos tries to first pull a vacuum so we don't have convection heat transfer because we have no fluid. But in addition, they make the surfaces facing each other in the thermos to be mirror-like. So that way we reduce the emissivity, and the heat transfer by radiation goes much lower. For example, if this mirror finish has an emissivity of 0.2, we would go from a 5 watts per meter square Kelvin to 1 watt per meter square Kelvin. 5 times smaller for radiation and negligible compared with the 10 watts per square meter and Kelvin of convection. Another interesting thing, if we are at high temperatures, 600 degrees, that is when things start to show like this dark red color from temperature, the emissivity, the equivalent convection coefficient for radiation is 10. So at 600 degrees, natural convection and radiation in a clean metal, they balance each other out. But if the metal got to oxidize, and those of you in MADI, you know that when you get things red hot in air, they tend to oxidize. The emissivity would be of the order of 0.9, and the heat losses would be of 50 watts per meter square Kelvin. In this case, we would see that radiation dominates over natural convection when we are glowing red hot in a dull material. Super interesting, because now we can start having enhancing our intuition of all things we knew, but we can assign some relative orders of magnitude and say what is bigger than other, how things compare. So, well, this is what I was talking, like on a surface that experiences both radiation and convection, which is pretty much every surface you ever see, right? In air, you can have an effective convection coefficient that is the sum of both, of the real convection coefficient plus the equivalent convection coefficient for radiation. It's yeah. I have a question for you. I just said that effective convection coefficient is H for the real convection plus H radiation, right? That is accounts for the equivalent convection of radiation. And I said pretty much every surface you see. Question to you: does this equation apply for heat transfer underwater, clean water, under clean water? I'd like to see maybe in the reactions, if you guys want to say yes or no. I have the list right in front of me, and I'd like to see what you think, if this equation does apply underwater or does not apply underwater. Yes, no? In the reactions, you can use the chat if you prefer. I'd like to hear from a few of you to have a sense if we're in the same boat here. I got a no. Thank you for that one. Anybody else? I got 2 yes. All right. So if we have a vote, yes is winning. Anybody else? One more. Well, maybe 2 more in case we have a tie. Okay, so now we have 3 yes and 1 no. So let's see, before I tell you the answer is, do we have radiation, thermal radiation through water? And I don't want to spend a whole lot of time waiting for the answers again, but the answer was no. The water is transparent to visible radiation, but thermal radiation is in the infrared, and water is opaque to infrared. So if we're underwater, clean water is the same under muddy water, and is the same as if it was under molten metal. For thermal radiation, water is opaque, and this equation 8 would not apply, because H radiation is 0 between surfaces that are separated by water. We said gases we are going to assume are perfectly transparent, which actually is a pretty good assumption. And we're going to assume that water and glass and wood and metals, all those are 100% opaque. We're going to see subtleties on that way later in the class. So as you see, the formulas are trivial, and even the concepts are trivial, but we need to put together a few things. And the issue of water or glass being opaque to radiation, that's not intuitive at all. Glass is the same as wood from the point of view of thermal radiation. Okay, another heat transfer mechanism, that is contact resistance. Contact resistance happens when 2 things at different temperature are in contact. Heat flows from hot to cold, but because there is an interface, the heat flows is slowed down by that interface. That's what we call contact resistance. And the reason I included it here is because the formula for contact resistance, without getting into the physics, which are amazing physics and beautiful physics, as the formula is the same as it's very similar to the formula for convection. The heat flux by contact resistance is proportional to the temperature difference between the 2 surfaces in contact. The 2 surfaces in contact are not at the same temperature. And this, the constant of proportionality will be H, an equivalent convection coefficient for contact resistance, which has nothing to do with the physics of convection, but has a very similar formula, H. The physics of contact resistance, and I think I have a schematic here. When we put 2 surfaces in contact, you think one air surface touches the other. But in reality, what happens is the asperities of one surface interact with the asperities on the other surface. So when you put two surfaces in contact, in reality, what you have is a bunch of points of contact. And as you can imagine, if I press more, I'm going to have more points of contacts, and the points of contacts I have, they're going to be flattened and increased. So with more pressure, the contact resistance is lower because the heat transfer is higher. Depending the type of material, depending whether we have surface contamination, there are a lot of things. The world specialist in contact resistance is a professor in Canada at the University of Waterloo. And he has written many papers in which he uses these concepts to make predictions. But to make a long story short, two metals with relatively clean surfaces, I'm not talking about like a scientifically clean, but two metals that don't look overly oxidized, if you put them in contact, they're going to have a contact resistance of the order of 10 to the 5 watts per meter square Kelvin. Oh, sorry, 10 to the 4 watts per meter square Kelvin. That's very high. Well, I said right, this equivalent coefficient, equivalent convection coefficient for contact resistance. So that equivalent convection coefficient of 10 to the 4 is very high. Convection in forced convection in liquids is 10 to the 3. So this is 10 times higher, right? If we were to have convection with phase change, like in an evaporator or condenser, that is 10 to the 4. This is what it compares to. So contact resistance tends to have like quite fast heat flux. So much like last time, if we say, let's do an example of two metallic surfaces in contact, one is at 40 C and the other is at 20 C, just as we have done for the previous cases, and the contact area is 1 meter square, calculating what's the rate of heat transferred across that interface. So we apply this formula, which in this case is trivial, and we get 2 times to the 5 watts, right? 200,000 watts. If you remember when we did the heat exchange by radiation or by convection, we got things of the order of 100 watts. 200 watts for convection, about 100 watts for radiation. And then this contact, the heat flux under contact is 200,000, 1,000 times faster. Right? To keep in mind the order of magnitude of the things we're talking about. Like exchange through surfaces is kind of slow, and exchange through these contact interfaces of solid to solid tends to be quite high. All right, and now we get into something that will be the topic of the next few weeks, and is after seeing convection, after seeing radiation, and after seeing contact resistance, that is the first two I'm sure you heard before. Contact resistance, probably you haven't heard of, but has the same formulas. So we got those. We are going to talk about conduction. And conduction is a completely different animal, because convection, radiation, contact resistance, all of those are associated with external surfaces, with surfaces going around the body. But conduction is inside a body. And the surfaces we're going to be talking about are like cross-sectional surfaces, are not outer surfaces. And people saw something empirically, and which we call Fourier's law. And what people saw is this, that the heat transferred by conduction, let's say we have a wall such as this. Let's say we have a wall, and and one side of the wall is at high temperature, the other side of the wall is at lower temperature. What people saw is the amount of heat transferred by conduction is proportional to the cross-sectional area. The cross-sectional area in this case is going to be all the area of the wall because the heat is flowing across the wall. So it's proportional. Bigger wall, more heat transferred. Smaller wall, smaller heat transferred. Right? Makes sense. Makes intuitive sense. So they say it's proportional to this area. It's also proportional to the temperature difference between the two surfaces. So if the wall is all at the same temperature, there will be no heat flux, delta T equals 0. If the wall has a gradient, there will be a heat flux. If I increase the gradient and the temperature difference between the two walls is higher, the heat flux is going to be more intense. And that's what this says. And in addition, what people saw empirically is that this heat flux is inversely proportional to the thickness of the wall. Something you know, because a thicker jacket loses less heat to the winter air than a thinner jacket, right? L in this case is thickness. Higher L means lower heat losses by conduction. Much like everything else in this class, you knew this, but we are putting it together in a way in which we can then make predictions that go way beyond intuition. So let's see. The way we express this is we turn the delta T into a differential of time, temperature. We turn the thickness of the wall into something very thin, and it would be a differential of X. And the heat per unit area becomes a heat flux. And this equation we have just discussed, equation 10, turns into this expression here that is called Fourier's law. Now we replace the proportional symbol with a proportionality constant. That proportionality constant, that is what we call the thermal conductivity coefficient, typically K. You're going to see pretty much in our book and pretty much all modern literature, people use K for that. And all it means is the proportionality constant between the heat flux and this is called the gradient. This proportionality constant depends quite a bit on the material, but to give you a sense of ballpark, the thermal conductivity of steel, it's a metal that is a good conductor, is more or less 60 watts per meter Kelvin. And the thermal conductivity of water is 100 times less, is about 0.6, right? So metals are very conductive, water not so conductive, and air has a thermal conductivity that is 20 times lower, right? It's 0.03. Air is a pretty good insulator. And that's the reason like Dawn jackets are so good, because you know what? It's not that they have feathers, it's what they don't have. In between the fibers of the feathers, there's air that is an awesome insulator. It's not the feathers, it's the air what is good for you, right? And that's the reason why some animals in cold weather, they have hollow hairs, because inside the hole, what is there? Air. That is an amazing insulator. Styrofoam. Why is styrofoam a good insulator? Not because of the polymer, but because of the air that is contained inside it. Awesome insulator. So let's do a calculation of heat flux by conduction. So the heat flux by conduction, the total heat by conduction would be the cross-sectional area, assuming is uniform, the heat flux is uniform over the area. You see I put AC because it's a cross-sectional area now, times heat flux. And you see that it has a subscript X, and the reason is that in difference than conduction, than convection or radiation, now conduction moves inside the body and can move in any of three directions, right? Can move in the X direction, Y direction, or Z direction. I'm going to discuss more about that in a minute. So in this case, what I'm saying is Q in the X direction. And why did I choose that? See, here in this schematic, we put the X direction as to going across the wall in the direction of the heat flux. Something I forgot to mention before, but if I go back to equation 11 here, we see something that is also, I never liked it, but I grew to accept it. And this can confuse people a lot. You see this minus sign? Why did they have to put a minus sign? Everybody does it, and I do. Let me tell you why I put a minus sign. So let's pick an axis, X, right? Positive heat flux will be when we move in the, heat moves in the X direction. Okay. Now, the gradient is a derivative, but see this, which is quite interesting. For the heat to move out in the X direction, what I need is that the temperature is hotter on this left wall than on the right wall. And here we have a schematic of the temperature gradient. And you get to see it's hot at X equals 0, and at X equals L is a little bit colder. This derivative, the delta T over delta X, is negative. So the heat moves in the direction in which the gradients are negative. So to say that my heat flux is positive in the X direction, I have to use a negative gradient. And for that reason is that we have this minus. So heat is positive in the direction in which the gradient is going down, is negative. That's why we have this minus sign here. And every time we put this equation in this differential form, we need to use the minus. Otherwise, we're going to get into trouble. So let's do a calculation. Q conduction, we said, is cross-sectional area. The proportionality constant, that is thermal conductivity, is the difference in temperatures on the surface between the two surfaces of the wall and the thickness of the wall. If the wall was 1 meter square in cross-sectional area, steel has a thermal conductivity of 60, give or take, but is what we use as a reference. And the difference in temperature was 40 degrees in one end and 20 on the other end. And the thickness was 1 centimeter. 1 centimeter of steel is quite a bit. That's getting into armor. And what do we get? That the heat loss with that temperature difference is of the order of 10 to the 5 watts. 1.2 times 10. So it's 120,000 watts. That's a lot. That's a lot. So what we get to see here is that the heat transfer by conduction, at least in metals, is very fast too. So we're going to see somebody asked me a question about, is it only for this case? But I don't know what it is. So if you tell me a little bit more details, I'll try to answer that question. So, the negative sign of the formula. No, always. And when you take the class on diffusion, you're going to see exactly the same. And this minus sign is always when you write this this equation in which you have a flux, in this case a heat flux, that is proportional to a gradient, but moves in the direction in which the gradient decreases. So you're going to see this exact same equation always in heat transfer, and a very similar equation in diffusion. All right, so what we're going to see later in the class is if conduction inside the body can be very fast and on the surface can be slow, like there is kind of a balance, right? Like sometimes if the body is huge, the conduction might be a real problem. If the body is really small, surface might be a lot faster in comparison. We will see how to handle those things. But you get a sense of how to calculate it, and in normal dimensions, how they compare with each other. I want to extend this very, very simple formula here. I want to extend it for the case in which we would have not just a very simple 1D heat conduction across a wall, which is a very practical concept, but it's also a particular case. Let's generalize it. And instead of talking just about the heat moving in the x direction, I'm going to talk about the heat as a vector. So that is the combination of heat moving in x, y, and z, right? That's why it's in boldface here, because it's a vector. And the gradient here that looks just like a derivative becomes this gradient operator. And you might have seen in your multivariate calculus, right? This operator, the nabla operator or the del operator. And I'm explaining it here. So okay. Okay. So the gradient is the derivative in the x direction times the unit vector in x, same with y, and same with z. You might or might not remember like this curly d, right? This backward 6, right? Means partial differential, partial derivative. If I have only one variable, x, for example, I have a total derivative. That's why it has the upright d. But if we have many variables, like multivariate calculus, right, x, y, and z, then we use the partial symbol. Why am I getting into this? I do love it, but it's not that's not the reason I'm getting into this. The reason I'm getting into this is because if we talk about cylinders, like guess what? Like tubes in a heat exchanger, or for example, spheres, which is a common geometry too, as we discussed on our example in the seminar on Monday, right? We start to have like some sort of 3D geometry. Not to mention that if you're going to be using computers, now you can have any type of geometry you want, and you better be able to calculate heat moving in different directions. Let's consider the case of a cylinder. The gradient in a cylinder is something you would do with using the Jacobian and change of variables. We'll do none of that. I know the answer, and I'm putting this answer for you. The gradient, when you're in cylindrical coordinates, has this expression here of equation 14. Similarly, in spherical coordinates, we are not going to do any Jacobians. We're not going to do any change of variables, but we're going to know that the gradient in spherical has this expression. Where I want to go with these crazy looking equations is that very soon on Friday, I'm going to show you how depending on the conditions of symmetry, we can cross lots of these terms, and our equation is going to become a lot simpler, and we'll be able to treat a 3D problem such as a sphere using a 1D equation, which is happy times. We don't want to solve equations, partial differential equations. Okay, so actually, I'm gonna start with this conversation now. When we have conduction that is three-dimensional, sometimes we have a dominant direction. So nothing is, everything in life is three-dimensional, but sometimes one of the dimensions carries all the heat, so much more heat than the others, that we can neglect the others. What are those conditions? One is the condition of symmetry. So let's say we have a cylinder, right? And in the case of a cylinder, very often, and we would have the gradient with this expression here, but very often in a cylinder, what angle we are in the cylinder, we have a symmetry of revolution. Symmetry of revolution, that means this term that depends on the angle in the cylinder goes away, and we turned a 3D problem into a 2D problem now. And here we have Fourier's equation for a cylinder with symmetry of revolution. And that was one of the reasons to show you this generalization to the gradient in the form of vector calculus, because this equation is a lot simpler than if you had to do the 3D problem. And in the case of a sphere, when we have symmetry, what we call spherical symmetry, we have this azimuthal and polar angles. And in spherical symmetry, there is no dependence on those angles. So this term can go away. This other term associated with the angle can go away. And we end up with only a derivative in radius. And here I'm calling myself a mistake. This should have been the upright D. I'm gonna need to update this note, because now the problem is a problem that is mathematically in 1D, but in physically it's 3D. Physically it's 3D because it's a sphere, but mathematically it's 1D because of the three coordinates. Two don't matter and only one matters. And life is a lot simpler that way. Let's stop here, and I'm going to finish this unit discussing geometry considerations and a few examples on Friday. Thank you, everybody. We can stop here.